Hello, we did Unit 10 and this is gas laws. A gas is something with no definite shape and it forms to its container, so it takes on the same shape. And a volume. Volume is how much space something takes up, and pressure is how often a particle collides with one another or when it crashes into something. And there's 7 gas laws, and they're ideal, Charles, Dalton's partial, combined law, Gay-Lussac's, Boyle's, and Graham's law of fusion. The first law we did was Boyle's law, and the equation for that is initial pressure times initial volume, and that equals the final pressure and the final volume. So we did here on the bottom the first example to show how to use this equation. And the example is a substance containing 4 milliliters of an unknown gas has a pressure of 10 atm. With the final pressure being 20 atms, what is the final volume? So what you do is you take your initial pressure, which was 10 atm, times your initial volume, which was 4 milliliters, and that equals your 20 atm, which was your final pressure, times your second volume, which we don't know, which is what you're trying to find. So when you plug all that in, you get 40 for the initial side equals 20 atms, and you still don't know your second volume. You divide that by your pressure on this side, and your final volume ends up 2 milliliters when you do the whole equation. So that's how you do Boyle's law.
Charles's law, and as the temperature increases, the volume increases also. This is also known as directly proportional.
Mm-hmm. And this is the equation for Charles' law, and it's the initial volume over the initial temperature over the final volume, or equals the final volume over the final temperature. So the problem we have here is an unknown substance contains 10 milliliters of H2O with a temperature of 50 Kelvin. Given the final volume of 20 milliliters, what is the final temperature in Kelvin? So again, the formula is here, and so you plug in 10 milliliters over 50 Kelvin because that's the initial volume and temperature, and that equals the final volume and temperature of 20 milliliters over T2 because you don't know the final temperature. So here you're going to cross multiply, and you get 10T equals 1,000. So you're going to divide by 10 on both sides, which gives you 100 Kelvin as your final temperature. Okay, this is the combined gas law, and the equation is P1 times V1 over T1, and P2 times V2 over T2. And the P's are the pressures, V is volume, and temperature is T, and the ones are like initial and final.
Okay, so our example for this is a gas mixture of carbon has a pressure of 10 atm, 15 milliliters, and 27 degrees Kelvin. And once more gas is added, the pressure is 15 atm, 20 milliliters, and an unknown temperature. What is the final temperature of carbon gas? So what we worked out here is you started with 10 atm and 15 milliliters, which is your initial carbon pressures and volume, and then 27 degrees Kelvin was your initial temperature. And that equals then 15, which was your final pressure, 20 milliliters, which is your final volume, and an unknown temperature, which is what we're solving for. So you're going to cross multiply. So you get 150T equals 8100, and then you have to divide by 150 to get T2 by itself, and you end up with 54 degrees Kelvin for your T2.
This is the ideal gas law, and the ideal gas law contains 5 variables. P, which is pressure, T for temperature, V for volume, and N for number of moles. And R is the ideal gas constants, which are these right here. And there are 2 rules. One is has particles with no volume, and 2 has no attractions between gas. and the standard temperature is 273.
Okay. The equation for the ideal gas law is P times V equals N, which was the number of moles, times RT. And for your R, these are these numbers right here, which will be given to you. You don't have to memorize them. But depending on in your equation whether they say ATMs, you would use this number for R. If it says kPa is your pressure, you use this number for R. And if it's mmHg, you use this number for R. So it'll tell you, which I'll explain when I do the equation, which one you'll use for this. So our problem says a mixture H2 and CO2 gases is combined in a 5-liter flask at 20 degrees Celsius. Determine the total number of moles if pH2 equals 1.8 atm and PCO2 equals 0.89 atm. So how you're going to plug this into your equation is you first have to find the total pressure. So what you do is you take the pressure of your H2, which is 1.8 atms, and the pressure of PCO2, which is 0.89, you add those together, and you get 1.6. So you're looking for your final pressure for the P. So you do your pressure, which is now 1.6 times the volume, which was 5 liters from our equation, which equals N is what you're looking for because it said find the total number of moles. So N you leave blank. Then this is where, when you're doing your R, this is where you use one of these 3 numbers. So in this equation, we're using ATM. So you come over here and you look for the one that's ATM, which is 0.0821, which is what I plugged in right here. Then after there, you come down and you're going to take your temperature, which was 20 degrees, and you have to add 273, and the K is kelvins. You always use Kelvin, to your temperature. So once you work all that out, you multiply these, which is 8. You still are looking for N, and when you do these two together, you get 24.05. You divide both sides by the 24.05 because you want N alone, and N equals 0.33 moles.
This is Dalton's law of partial pressure, and in the mixture of gases, each gas exerts its own partial pressure, and it adds up to a partial pressures to get the total.
Okay, so the equation for this is the total equals just all the partial pressures added up. So we have a problem. It says a container has oxygen and helium. The total pressure is 300 kilopascals. What is the partial pressure of helium when the partial pressure of oxygen is 170 kilopascals? So you're going to add oxygen and helium together to get 300 kilopascals. So 170 plus the partial pressure of helium equals 300, so you subtract 170 from both sides, which leaves you with 130 kilopascals for the partial pressure of helium.
The third law is Graham's law of effusion and diffusion. And diffusion is the movement of particles from a higher to a lower concentration. And effusion is gas particles that escape through a tiny hole in their container.
Graham's law's equation is the rate of the faster gas over the rate of the slower gas. And you're going to square root the molar mass of the slower gas over the molar mass of the faster gas. And you have to remember when you're doing molar mass, if the element is diatomic, you have to make sure that you do the diatomic part. Okay, so our equation that we did for this, our example, is calculate the ratio of the velocity of carbon atoms to the velocity of helium atoms at the same temperature. So carbon is diatomic. So on the bottom, you're going to put your faster rate, which was 24 grams per mole, and then you put your helium, which is the slower, on top, which was 4 grams per mole. And when you divide and square root that, carbon is 0.408 times faster than helium.
This is Gay-Lussac's law, and as the temperature of a gas increases, its pressure increases at a constant volume, and that is directly proportional. And STP is standard temperature and pressure, which is 1 atm is equal to 0 Celsius.
Okay, and the equation for this is P1 over T1 equals P2 over T2, and that's the initial pressure and temperature and the final pressure and temperature. So the problem we have here is a gas starts off with a standard pressure of 1 atm at 10 degrees Kelvin. If its final temperature is at 10 degree or 100 degrees Kelvin, what is the final pressure? So you put 1 atm over 10 degrees Kelvin because that's the final pressure and temperature equals P2 over 100 degrees Kelvin because that's the final temperature. So you'll cross multiply these and then you get 100 equals 10 P2, and so you'll divide by 10 on both sides to get the final pressure by itself, and the final pressure is 10 atms.
And then on the bottom you put the rate of the second gas on the bottom, which will be your slower gas. And then you're going to do square root here. So it's kind of like cross multiplication. So you're
Graham's law. I was trying to get my thoughts there. I'm sorry. Graham's law contains diffusion and effusion.
equation is the rate of the faster gas over the rate of the slower gas. And you're going to do
The little dividing thing, the little thing you squared.
It's called a square root symbol.
Are you recording?
I am.
and that's carbon. Carbon is the faster gas.
We did Grant.
Show up on the boat. Like, okay, because we'll be, like, on my boat, and then there's, like, these bugs that are, like, have all these arms, and then they'll, like, land on me, and then, like,
No.
No?
No, not those.
Oh. Then what are those?
I don't know, but not those.
Then what are those?
I don't know.
Did they come from the water or something? You need to raid them things.
I know, they come with the fish. You can eat those.
No, you can't.
Yeah, you can.
No, you can't.
Yeah, you can. You can cook them.
Cover my
But nobody,
chocolate?
but nobody,
Yeah.
like,
Whatever
Africans
works.
eat those.
Africans.
Yeah.
Africans?
Africans.
My dad lived in Africa. I don't think he ever ate bugs.
You never know.
They
This
eat
is
bugs.
true. This is very true.
You never know.
Alright.
Once
Dalton's
again,
law
back
of
to
partial
chemistry.
pressures.
How you off this floor? I'm scared of that bug.
As you can see, this is what we do to make our chemistry project.
Dalton's law of partial
You think it up.
Dalton's law.
How can that bug sting you? It, like, bite you or something? Like, how does that work?
How do you get on these bugs? How do you get on these
so
bugs?
weird.
You're so random.
That thing was so weird.
We're talking about chemistry.
But you're so random.
Dalton's law.
Nothing.
No, it's good.
No.
What's in that water?
Nothing.
Uh-huh.
Okay, so what Jasmine said was, are there fish in that water?
I'm pretty sure that's how that went down.
Yeah, because this is Aaron's house, and Aaron's house is on the lake where fish...
Right, and we are working on a chemistry project, and we're talking about fish in a lake.
Yes.
Right.
And then she said,
I'm done.
can you eat those fish?
Right, because you don't eat fish.
No.
You know.
I mean,
Right.
chemistry.
Yeah, back to chemistry.
Chemistry.